tilted, it doesn't have to be circular, it doesn't even have to satisfy, it doesn't even have to be concentric with respect to the line. Right? Just okay, and you can generalize this into any current. And they can be pointing in different direction if you want. And this is also equal to mu naught sum over. Okay. So that's Ampere's law. And so this is basically very similar to your Coulomb's law in electrostatic, right? That's your analysis here. Electrostatic. Okay. Recall, in electrostatic you have the divergence of E is equal to, so perhaps 1 naught. This is equivalent to a statement that says that this is Gauss law, right? A is equal to 1/1 naught. And another statement, you're more familiar with this, EDL, right? This is the two equation. And this is equivalent to saying that the electric field is minus the gradient of potential. And then this is also equivalent, which we do later on in the lecture, that the curl of E is equal to 0. Okay, and let's collect what we know from electrostatic for now. And the first thing is Ampere's law. L is equal to mu naught. Okay. Now, just to generalize, here, by principle of superposition, you have that, right? But let me generalize. Instead of having wire carrying current, let's talk about current density. If I have any surface bounded by C, right? This surface, this is that one. Any surface like that, surface S, okay, bounded by C, okay, then the current on that surface, total current, I enclosed by C, right? This is just integral over S, J, right? But this is the current density. Okay, and we know in this case here, because it's a steady state situation, right? This integral here is independent, so let's draw the same C again, the same loop C, right? It's independent on what you can use a flat surface, right? Or you can use any surface you want, as long as it's bounded by C, right? Any surface. S, S or S prime, as long as through is because suppose I have two surfaces, right? Let's call this, suppose this is the same C, right? This is S1, this is S2. Okay? So the normal, let's point the normal of this surface all along that direction. Okay? And then the normal of this surface also point in that direction. Okay? Then the integral, let's just write the integral over S1 of JDA, right? Minus, right? In this case, I want to do minus. Say, plus the integral over S2 GdA, right? So if I look at the flux of the current through S1, right, and plus the flux of current through S2, this is this flux of current. Okay. This whole thing has to be equal to the closed loop flux, right? Okay. And this has to be equal to, this is all the flux that come out from a closed volume, right? That has to be equal to minus dt times the integral of the, right? The total charge inside. And in the situation when you have a steady state, this time derivative is equal to 0.
Wait, so do these have the same boundary?
This has the same, yeah, the surface has the same boundary,
okay,
right? But it has different, one is, imagine having that soap bubble, right? Bounded by a perimeter, and then you can have a flat surface of a soap or something, you can blow it and you have another surface, right? So I have two surfaces, one S1 and this is a flatter S2, right? And because this is equal to 0, you have a steady state, then integral over S1 JdA has to be equal to minus an integral. This part is 0, right? JdA over S2. Okay. So, the thing is, you have to be careful about the sign, right? Because if this, sorry, this is a minus sign, because I want a closed loop flux over a volume, right? So if that's outward this way, right? This is the same surface, then normal is all outward that way, right? Okay. Anyway, I think I'm not explaining myself very well here, but one of this degree has become plus. This should be minus. Okay. So it doesn't matter, the conclusion is that it doesn't matter what surface you use, right? As long as it's bounded by C, you have the same total current ingress, right? Because of the steady state. Okay? So, with that, I can express the Ampere's law. If I have a surface, then the Ampere's law says that the integral of L around C, right, around this closed loop, right? By the way, you also have to make sure that you're consistent, right, with the right-hand rule, right? C, if you define C, you have to have a circulation in this direction, right? Then normal is in that direction. Normal of that surface is in this direction, right? This is where the minus sign comes from in this case. Well, I don't want to go through this again because I want to move on. That has to be equal to mu naught times an integral over that surface J. And you have to be consistent. This TA has to be pointing along the normal, just by the right-hand rule. This is C, if C is in the direction of your fingers, then N is in the direction of your thumb. Okay? So that's Ampere's law. Okay, so let me change that to make it more general, which is an integral of J. So for S, this is over C. Okay? So that's actually not enough. Yes, please.
Wait, so on that board when you're going through the steady state, do you just mean that if it's a closed surface, then it'll be zero? Because in this case, it's not zero, right?
In this case, no, I just want to show. I mean, this just shows that it doesn't matter what surface I take.
Oh, okay.
Right? I'm just trying to say that, well, it's general, right? If I have a bounded curve C, right, then the current through it, that bounded loop is independent of what surface I use. Okay. In a situation of steady state, when t1 to t is equal to 0. Okay. It turns out this is not enough to define the magnetic field, right? Just as in electrostatic, we have two equations. Here we only found one so far. So let's go back to our original example and generalize again. I. Here we found that the field is V naught I over 2 pi R. Okay. So if I look at it from the top,
it's okay.
Right? Okay, so the P field it actually looks like here. Right? And this thing goes as well as one of the top. Right? So unlike in electrostatic, sometimes you have example where you have a point charge here, and then all the electric field points radially outward. Right? And this is how you get Gauss law. Right? In this case here, the P field instead of being radial, is actually tangential. Right? And if you calculate a Gauss law for this situation, right? If you impose this current with the cylindrical surface S, let's call this Gaussian surface. Just to make sure, right? It's nothing to do with that surface for Ampere's law. Right? If you impose this current concentrically with the Gaussian surface, then over that surface S goes to BA, right, is equal to 0. Right? Because the P field is tangential, right? And then the flux, there is no flux. The flux is along the direction of the normal surface. Okay? No flux. Okay. And the reason for this is because fundamentally there is really no reason for this, but the Maxwell equation, it turns out there is no such thing as a magnetic monopole. Right? With the charge, you have a monopole. You can have a point charge, and they all radiate outward. The field radiates outward. But for a magnetic field, you don't have that. There is no monopole. There is no, what do you call it, constant times you don't have that here. Okay? So that's why this is 0. Okay? And if you write this differentially, then this shows that the divergence of B is equal to 0. Like this is equivalent. Just like Gauss law for electrostatic here, right? Is equivalent to the divergence of E is equal to rho over epsilon naught, right? And the picture that we keep in mind is this picture, where the Q and the electric field is all radially outward, right? For a magnetic field, this is the elementary picture that you want to keep in mine, they have current, right? And all the field is tangential. The divergence of B is 0. Any questions so far? And this is, once we general, of course, we found that for a particular case of an infinite current, right, along Z, but you can generalize that and elevate the equation into a status of law. There is no name for this, unfortunately. But L is equal to 0. This is equivalent to saying that the divergence of B is equal to 0.
Should that be a dA?
Sorry?
Should it be dA?
Oh, yes, you're right. This is I'm probably more prone to make a mistake because I don't have my notes. So let me know if I make a mistake. So let's see. With these two equations, we can actually solve a lot of simple symmetrical problems, right? Just like in electrostatic. In fact, mostly with this Gauss law, but maybe a little knowledge of this integral. Line integral of E is equal to 0. You can derive situation with planar symmetry, right? Spherical symmetry and cylindrical symmetry. So in this case, let's try to do the same for magnetic field with symmetrical configuration. First of all, we already know one example that line, that current, right, along the Z direction. The next example is solenoid. Okay. So solenoid is actually used a lot. This is not a solenoid, by the way. This is actually a resistor for the purpose of the demo. But the solenoid is basically something that looks like that, right? You have a wire that you wind around in a circle, right? So better representation of it looks like this, right? Kind of look like a solenoid. So what you have is, I want to make sure that my second rule is correct. So I have current, okay, and I wind it into a cylinder, right? A cylinder, say of radius R or A, okay, and length L, okay, and there is current is I naught, and there is a winding density. And density of N, right? Meaning that there is N loop per unit length. Okay, let's find the magnetic field everywhere. Okay, look at it from the top. You see something like this. If I look at it from the top, I hope the drawing makes sense. There is current going that way, right? So the current goes this way. Okay. It has a circular symmetry, cylindrical symmetry here. First, because of symmetry, right? The B field cannot be tangential. Let's do the easier example. The B field cannot be radial. Right? Because if it's radial, right, then it has to be radial everywhere by symmetry. Right? In that case, then from Gauss law, I can bring the PR out again, right? And integral of A, right? Because of symmetry, I can take this out because it's constant. over this surface, right? And this has to be equal to 0, right? Because of this law. The derivative of this is equal to 0. Okay? Therefore, PR is equal to 0. No radial component of P field. Also in this case, right? Not just in the case of a current going in C direction. How about the P field in the tangential direction? Again, if this is the loop, right? Current I. Let's consider if I have a P field in the tangential direction, right? And by symmetry, they're the same, right? It's constant. Then I could do the same thing, but not with the Gauss law, with the first law, right? The Ampere's law. Integral of P dl. In this case, it becomes just integral of, I can take out the magnitude of the P field in the tangential direction. Is equal to mu naught times current enclosed. Good. There is no current enclosed here, right? It doesn't matter. Even if you're looking at the P field at the point outside of the solenoid, say R is outside of the solenoid, right? I can do the same thing. Right? I can this curve here can be inside or outside, right? There is no current enclosed. Because in this case here, the current is only circular, right? So there is no current going in that direction. Of course, that's not completely too experimental with that, because when you wind a wire, when you wind a wire, like this is perfect. I have this, right? So there is some residual current going up, right? But there's a fringe effect that I don't want to include right now. I will address it again later, right? But let's pretend that you can idealize this, that there is no, the winding is completely circular. Then the current enclosed is 0. Therefore, the P field tangential is 0. Right? Okay? I'm going through this slowly because this is really important. As far as the derivation go, and also, it's important for you to know this to solve problems. Okay, so we are left with the last component of magnetic field, right? The component, because the tangential is 0, radial is 0, we are left with DC, right? Okay, in the C direction, right? In this case, the argument is not as clear, but let me convince you by saying, so this is solenoid, that if there is a P field, the P field outside is going to be 0. Because far away, equals to 0. Okay? And it's not quite clear why, and maybe I can back to another example later on. But let's take it as an experimental fact that the P field far away is 0, right? Then I can do the same thing with the Ampere's laws. Right? If I take a line integral like that, C, okay? Then this is component 1, 2, 3, 4. Right? Component 2 and 4 is 0. Right? It's identically 0 because there is no P field in the radial direction. Right? Okay. In component 3, is equal to 0 because it's far away. Okay? So you're left with the component 1 Also by symmetry, this thing is infinite, right? So it doesn't matter whether you're here. If I have a PC, right, it doesn't matter whether you're here or you're here, it's the same, right? Because of translational symmetry in this direction, right? So I can pull the D out of this integral. C L over 1, right? And the whole thing has to equal 0. That should be equal to parameter close, which is always 0, right? So therefore the B field inside, the B field outside, anywhere outside is 0. Right? So it's 0 everywhere, basically. Right? The issue is what's inside. Right? Inside, again, this is the winding density and look per unit length. Let me know if you have any questions by the way. Then if I construct a loop like this, okay? 1, 2, 3, 4, right? And the integral of PDL is just an integral of P1 of surface of loop 1 PL, among loop 1 and segment 1 PL, right? There's 0 everywhere. Because the P field at 3 is 0, right? Okay, if you do that 2, cannot be regular, okay? And this whole thing has to be equal to mu naught iron force. Now what is iron force here? Iron force is if this thing has a length L, right? Iron force is the number of bonding per unit length. Right, times I naught, right, times L. This just tells you the number of loops over the length L. Right? And the left side, right, is just an integral of P1, or this PL, right, P1 or segment 1, right, and this integral, I can get this B out, which is BC, right, times F. Equal to mu naught and naught. PL cancel. The magnetic field inside the solenoid. BC is mu naught and naught. It's clear so far? Right? Any other questions? Any questions? We generalize this. Not generalize this, let's start with another example. The next example is, suppose I have a sheet of current. In that direction. And this takes a current density, surface current density. It turns out we shall call it J. With this kind of funny script J. Say, what script is this, do you know? It's a current script, right? J, that's denote a surface current, not volume current density, right? Surface current density, just along the sheet. This is analogous to sigma in your case of in the electrostatic case of surface charge density, right? And it's going in that direction. Let's define a direction. Let's call that this is Z. X and Y. So there is a surface current J going in the Y direction, right? Okay. And we want to find the magnetic field everywhere. By the way, just to look at the example, if you don't like the fact that this winding gives you residual current in the z direction, right? You can also think of wrapping that that surface current plate, right? If I have that surface current plate, and if I wind it into a circle like this, right? Okay, like going that way, so there is a current density like that, right? J. Okay, so same thing here, by the argument of the Ampere's law, right? You can follow the same argument and show that the field inside is going to be in the z direction. By the way, it's constant everywhere. Right? The field inside the solenoid is the same everywhere. It's mu naught and I. Okay? But if you use this surface current sheet, then loop it around into a cylinder, then Vc becomes mu naught, right? J, just like this is right here, okay? Vc times L is equal to mu naught J times L, right? Okay, then Vv, in this case, the L cancel, it's just mu naught J. Okay? Unit is correct, right? Because this is the number of winding per unit length times current. This is just current density, right? By the way, this has unit of ampere per meter, right? Per length, right? Because this is current density, not charge density is charge per meter squared.
How did the units work out in that equation? Because because Ampere's law says like
yes.
Wait. Okay, never mind. Sorry.
Right, because I'm creating this loop, right? That enclose N piercing, N times L piercing of this current through C. Okay? So back to our example. In this case here, okay, what's the P? Okay? I should have done this tilted that way, but it doesn't matter. First of all, there cannot be any field in the x direction as example is here. Again, by symmetry. Right? Because if you have that, then you cannot satisfy the equivalent Gauss law with the B field. Right? If you have this, then the divergence of B is not zero. Okay? So Px is 0, right? And also there cannot be Py. Py has to be equal to 0 by the same argument of Ampere's law. If I look at this current, right? If I draw it from the top, looking from the top, it's a sheet. Right? And then there is current going that way, right? So if there is also this is the direction of y, right? If there is a B field in the y direction, then it has to be the same everywhere, right? I cannot